In this lesson, we will build an intuitive picture for how membrane curvature emerges on nanoscopic scales. We'll go step by step, from smooth shapes we see under the optical microscope down to nanoscale patches where thermal motion roughens the surface, and then up to the mesoscale concepts of mid-surface curvature, bending rigidity, and tensionless states. We'll also see how small solutes generate spontaneous curvature with opposite signs for adsorption and depletion, and finally how molecular simulations help us explore complex membrane processes. On the micrometer scale, biomembranes and vesicles look smooth and gently curved. Here is a vesicle, a nearly spherical closed membrane. Even though it can adopt many non-spherical shapes, at this scale its contour appears smooth, so we can describe it simply by its curvature. Let's add a 1 micrometer scale bar to fix the scale in mind. But at nanoscopic scales, each lipid and protein undergoes thermal motion, both parallel and perpendicular to the membrane. Perpendicular displacements act like tiny protrusions that roughen the two interfaces. To talk about curvature, we average over conformations within a small membrane patch. Molecular dynamics shows the minimal lateral patch size is about 1.5 times the membrane thickness. For a thickness of 4 nanometers, that gives a minimal patch size of about 6 nanometers. That patch contains roughly 80 to 100 lipid molecules. So curvature is an emergent collective property. After averaging within the patch, we define curvature on the midsurface, right between the two leaflets. We now define curvature on the midsurface. Imagine a small curved membrane strip with 2 leaflets and a dashed midsurface between them. The resistance to bending is quantified by the bending rigidity, kappa. Curved conformations are only accessible when the membrane is effectively tensionless. Formally, the mechanical tension should be small compared to kappa over A, where A is the area of the membrane segment. We express this as tension is much less than kappa divided by A. For a typical segment, kappa divided by A can be about 0.08 millinewtons per meter. These tensionless states serve as the natural reference to extract bending rigidity from undulations, the Gaussian curvature modulus, and spontaneous curvature. Small solutes can generate spontaneous curvature. Attractive solute membrane interactions create adsorption layers adjacent to the leaflets. Repulsive interactions create depletion layers. We'll visualize both cases side by side with an external solution at the top and an internal solution at the bottom. These two mechanisms produce spontaneous curvature with opposite signs for the same concentration difference. In both cases, spontaneous curvature varies linearly with the concentration difference between exterior and interior. That is, C0 is proportional to delta C. Molecular simulations have transformed membrane biophysics. Up to 1995, there were only a few hundred studies. Over the next 20 years, more than 25,000 publications appeared. Let's sketch that explosion. Simulations let us watch processes like membrane fusion or membrane adhesion via receptors and ligands, and even adsorption of polymers like PEG onto ordered and disordered membranes, helping us compare their free energies and typical conformations. Summary: on the micrometer scale, membranes are smooth, and we describe them by curvature. On the nanometer scale, thermal protrusions roughen the interfaces, so we define curvature by averaging within small patches that contain many lipids. Curvature is set on the midsurface. Bending rigidity quantifies resistance to bending, and curved states appear for tensionless membranes when tension is much smaller than kappa over. Attractive adsorption and repulsive depletion of solutes create spontaneous curvature with opposite signs, both varying linearly with concentration difference. Finally, molecular simulations now let us visualize and quantify complex remodeling processes like fusion, adhesion, and polymer adsorption.